I'm going to pull a moment to start. Before we get into the last topic for the midterm, let me just mention quickly, let's see, that so I posted like a couple of minutes ago an announcement. If you read the syllabus, there's like part of the class of the grade which was related to some written assignment. At the end of the day, like what I'm doing what I'm making the written assignment is just like asking you to watch like 4 YouTube videos throughout the semester. So, well, you can read the details for the assignment here. I posted it on the same Canvas site where you find the conceptual problems. So the video itself is actually like 20 minutes long. So it's not like it's not like a assignment or anything. In fact, I tell you on each where to find like the answers to the questions according to the on the video, like around which minute like they give the answers. But I suppose the like intent is like for it to be about something that seems more useful that like sometimes we discuss. So this first video is related about gradients, like the same gradients that we're talking about in class, and neural networks. And neural networks are like the thing, I don't know if you know about machine learning or that's sort of like the way in which you make like computers or algorithms recognize like say things like images. So when you have like if you have like an iPhone, you have seen like this feature where like it can recognize your face to instead of like you typing like the password, right? Like so that you can access the contents of the phone. And so like image recognition is like a big thing in computer science. And so that's actually like the way it works is related to gradients. So you can watch it. It's a cute video, and the questions are relatively straightforward. So if you have if you get the chance to watch it before the exam, I actually think it's useful. But I mean, you can watch it later because it's due on the 25. So just pointing that out. So today, basically, we're going to talk about the last topic for the exam, which is about optimization. By that, I just mean like how to find max and min of functions. So I don't know if you remember from Calc 1, what was the situation in this case? So in Calc 1, you will have like maybe a function like this. And like you say want to find like the max and min of this function. So there seems to be a min here, right? And it looks like maybe there's a max here. And I think it's fair to say that there's probably another max around there, that point. So this should be like a max, and this should also be like a max. And so if you remember, the first thing to even finding this is like that you would find the critical points, right? So as I explained, well, today we're not doing review because we still need to finish the material. And then on Monday, we do have to start new things. I'll give you extra office hours on Monday, and also tomorrow, Tariq, the TA, will give you extra office hours. But yeah, so we don't have a review per se. So the right, like first you would find the critical points, which is where the first derivative is 0, correct? And after you found those, and like we sort of did that last time, but we will do this again with some new examples for our situation, where instead of like the first derivative being 0, like the analog for us is like the partial derivatives are 0. Okay. But like the more interesting part for which that you would do later is to know if you had like a max or a min. There were a couple of ways, but the one that is actually useful for this class is like the one that looked at the second derivative. And so I don't know if you remember what the sign of this, let's say that this point is called P. What is the sign of the second derivative of the function? In this case, yeah, it had to do with concavity, correct? So what was the sign? What sign must the second derivative have at this point?
Positive.
Yeah, it had to be positive. I like this trick. Well, they're like saddle points will appear, but in this case, like this would be a mean. Like there's something called saddle points, but that's a different one. Like saddle points is more like inflection points. So like there will be three things: max, mean, and saddle points. Saddle points were like the potato Pringle chips that I showed you last time at the end of class. So then the mean, right, it had positive second derivative. One way to remember it, I don't know if that's how you saw it, but if the sign is positive, then you can make a face, an emoji, and the emoji is positive, so the eyes are positive. So that means that you're happy. And if you're happy, you get like a mean, right? So you make an emoji whose mood is given by the sign of the second derivative. So in this case, like say if you call this point Q, then, well, as you may imagine, thanks. As you may imagine, the sign now is negative, right? Like at a max of the second derivative had to be negative. And so that you see that this works actually, right? Like, so the emoji now has negative eyes, right? Which means you're negative, pessimistic. And if you're pessimistic, then like you get a max. Sort of opposite, like, you know, it goes contrary to maybe what you would expect just in terms of the language, right? If you're pessimistic, you get a max. If you're happy, you get a min. But I mean, well, let's let's be optimistic. So good. I mean, I think that's a fun way to remember it. Something similar more or less works for the case we are interested in. It's just that, you know, we have more than one second derivative, because if you think about the second derivatives, we could do them against xx, xy, yx, although those two were the same, and yy, right? So so let me tell you what the second derivative test is for us. And this is really like, think of it as a black box. Like if we had more time, like we could explain why it works, but this is just like a piece of information that tells you how to think about this stuff. So before doing that, like, let me just say what critical points we're dealing with. So again, like there are three types of critical points for us. So critical points now here means that, you know, the partial of f with respect to x is 0, and the partial of f with respect to y is 0. When we're doing this, like all our functions will be functions of two variables. So that's like the only thing that we are going to analyze in this class. So now when I say critical point, again, I just mean that you said the two partial derivatives equal to 0. I'm going to do some examples about this in a second. But and then again, you have sort of three situations. One is like a local max. Local max, think of a of it as, I mean, it's like a peak of a mountain, right? Like top of a mountain. So it looks like something like this. And a local max just means that as you approach, like, you know, in order to reach the local max, you always need to climb, go up, right? Like you need to climb. So as you approach the max, this point, the value of the function increases, or another way to say it is that the value of your height increases, right? Your height. If you think about it in terms of the height, right? If you think of the graph as giving you a mountain, a terrain, then the other extreme is like the local mean. So for a local mean, oh, it's like a valley or something like that. So like the bottom, like you just turn it upside down, right? So here it is. And you see, as you're trying to walk towards this point, there's no way to reach it without like decreasing your height, okay? So as you approach this point.
Just a quick question.
Yes, yes.
So for both the local min and local max, both partial derivatives or all partial derivatives should be zero?
The first ones, yes.
The first partial derivatives of all variables?
Yes, with respect to both variables, correct, yes.
Okay.
If you had, like, say, a function of 4 variables, right? You said each of the 4 partial derivatives equal to 0, yes.
So then the only way to differentiate them is when one is like going lower than the max value and the other one is going like higher.
I mean, the way which, I mean, that's like the definition, but the way which we differentiate them is through the second derivatives, right? So
okay,
yeah. So the second derivative, like, you know, the first derivative identify, it's like like, you know, like a detective work, right? With the first derivative, you identify the suspects, and then you apply the second derivative test to see if you're the murderer or you're innocent.
Okay.
Right? Like, I don't know which one, like what corresponds here to be a murderer, but I mean, yeah. So it is, the detection comes with the second derivative test. The identification comes with just setting the partial, like the first derivative is equal to 0.
Got it. Thank you.
And then there's this other one called the saddle point, which I sort of showed you last time. This one is always difficult to draw. So that's why I showed you the animation last time. I don't know if Pringles, is this how you spell them? I should have bought some, but. Right. It's a horse saddle also. I mean, actually, that's why but I mean, I think horses are like, I think in our modern society, people are more used to Pringles than actually seeing a physical horse. So yes, so it just means that, you know, if you have a point here, it just means that if you have a point here, like, you know, there are directions where you will see like you have to climb to reach this point, but then there are other directions where you feel like you have to go down to reach this point. So it sort of is like a max or a min depending on how you approach it, basically. So it just means like somehow that there will be like directions where you feel like you're climbing, and there will be other directions where you feel like you're going down. So it's sort of like a max or a min. It behaves like a max or a min depending on how you approach it. That's like the way to put it. uh, okay. Yeah, they're difficult to draw. I mean, at times, like depending on the day of the semester, like on which semester I have done this, sometimes it comes well, but today is not one of those days. So, so this is are like the critical points. These are like the three types that we would run into. And now comes the important part, which is how do you actually know? Yeah, no, I actually was thinking I don't have a Pringle prop. In fact, I don't know why. Like, I'm thinking whether I have something right now that is like Pringle-like. But I mean, the closest thing is like a donut. Say if you had like, I think a donut more or less works because if you look at a point on a donut, like, you know, there are directions where you sort of feel like you're climbing towards this point, but then there are other directions like, well, maybe no, maybe the donut is not even that good. Like, let's go to
what about the inside of the donut? Like one of the inside.
right, like the inside of a donut. Yeah, that's actually better. But let's just cheat a little bit and let's go to. I mean, this was like the classical example of a saddle point that I showed you last time. So let's just do it again. Yeah. Sorry. Let me go to GeoGebra. I mean, it would be a virtual prop, but I'll have some Pringles next sometime for the near future. So you see, like the if you think of the critical point as being the origin here, then say if you're, it's like rolling down a ball right through gravity. So if you place like a little marble on this part of the surface, it has to come down, right, in order to reach this critical point. But if you look at it from another side, another point of view, like if you place a ball here, you actually have to go against gravity, right? Like you have to increase its height in order to get to the critical point. So I don't know if you see like that it actually depends on which, how you approach the point that you would feel your height increasing or decreasing. Is that making sense?
Wait, so it's just the middle of the curve?
The critical point would be this point, like the origin itself.
Okay.
I'm just saying that the critical point is a point, right? So it's just one point on the surface, right? I'm just saying that what makes it a saddle is that if you want to get to this point, sometimes you have to come down, right, from the surface, and sometimes if you are on the surface, sometimes you have to go up to reach this point. So imagine like you're just like finding a treasure, like here's where the treasure is, but depending on where you started on the surface, you would see your height decrease or increase. Is that making sense?
Okay. I just thought of one other thing. So 1 second. One of like the odd graphs, I think it was y to the 3. Wouldn't it look like x to the 3? Wouldn't it look like that? Like one side it goes down, the other side you could go up.
Well, let's see. You're saying like, by the way, just before I tried that one, this is like a mean, right? Because you see this one, like the origin is like the critical point, but if you want to get to the origin now, you always have to come down regardless of where you are on the surface. Now, the one you're saying is something like y to the x, like to the 1/3 or something like that.
No, I just meant like y equals x to the 3, like the third power.
Oh, okay. Oh, right. Like that would be for the case of a function of one variable, right? Here we're looking at two functions of two variables, but yeah, we can still like this one. Right. This is like this was like a critical point, right? Like at the origin. it is like saddle points are sort of like what was known as inflection points before. If that helps a little bit with the terminology. So yeah, you're correct. Like in this one, if you are approaching the point from the right, now the point would be at the origin, right? So if you're approaching this point from the right, you see you have to decrease your like the value of the function. But if you're approaching it from the left, the function is increasing, right? Is that making sense?
Yeah.
So right, a saddle point is like the grown-up name for inflection points, kind of. So yeah, this is like, I mean, not this picture because like I already erased it, but yeah, like this is like surface version of what happened in this curve. Like it just depends on how you approach it, that you'll see like a max or a min. Like here you see a max, but here you see a min, basically. It's something similar here. Is this making sense to everyone? The good thing is that it's not that you're going to visually figure out what it's supposed to be. This is something that the second derivative will tell us. So here's the second derivative test. So in the first step, you find the critical point, right? You find a critical point. This is again where like the first partial derivatives vanish. We'll do this with an example very soon. Now, here's the cool thing. I don't know if you remember, you have that I mentioned that there are many second partial derivatives you can find, right? But you can arrange them in a 2x2 matrix, right? This matrix is called H. H stands for Hessian, but you don't need to know this. So the H here but it is very similar to what we did in before. So what you have to find is the determinant of this matrix. So this means find the determinant of the matrix at the critical point. So this is the value. Okay, and it will be a number because I don't know if you remember, like the determinant of a matrix is just a number. So this is a number. And there are like, you know, as a number, there are a couple of things that can happen. And there are three things that we care about in this case, like that this number could come to be 0. And if this number comes out as 0, then it's game over. And by that, I just mean that the test becomes inconclusive. This is analogous. I don't know if you remember, like when the second derivative became 0 when you were doing the second derivative test. So here, this test is inconclusive. So you can't use the second derivative test and you gain no information. Then the other easier case, and again, we'll do this in a moment. The other relatively easy case is when the determinant is negative. So this is a negative number. And if it happens to be negative, the critical point P actually corresponds to a saddle point. So here you get a saddle point. And finally, the last case is when the determinant is positive. And then if you have a positive determinant, you have to look at now at the second derivative with respect to x. So if the second derivative with respect to x is positive, I don't know if the emoji trick still works. So this is positive. And so P is a relative max. And if the second derivative with respect to x is negative, the emoji still works. So, this is a wrong emoji, right? No one stopped me. Is this better now?
Yes, thank you for catching it.
Yeah, no, you should yell or something. This is like an emergency. So yeah, good. Okay, this is all that you like. I mean, at least you have the advantage that you have like this note sheet you can use on the test. Like I would almost tell you copy paste like this thing. This is
So,
crucial.
I have a question.
Yeah.
So when you have a positive determinant, the rest of your test only consists of checking the second derivative in the x direction.
Yeah, you could also state it by looking at the second derivative in the y direction, but it's just easier to do it in the x direction because that reminds you more of the Calc 1 situation. But yeah, you just have to look at one of them. Yeah.
And if we've already checked the determinant of h of p, then will we already have calculated that second derivative in the x direction already, or no?
Yeah, you end up doing it, but let's do an example so that everyone sees how in practice this works, if that sounds good.
Why does this seem a lot easier than how we did things in Calc 1 and 2? Isn't this supposed to be the harder one?
Well, yes, but also like, you're comparing your learning at different points in your life, and so it is hard because you have already internalized the Calc 1 lessons. So, I mean, it doesn't need to be, that's a good thing, right? Like the successive material looks better, or easier. So, but good. I mean, it like a lot of the philosophy of multivariable calculus is all that you already did in the past, is now that you just have more variables, right? So if you think about like actual skills that you have learned, you almost have learned no skills in this class. I don't know if I should be saying that, but I mean, you're still finding derivatives in the same way as before. You're still finding integrals in the same way as before. It's just that now maybe there are like more like letters involved, right? But in terms of like actually doing new things, like you're still sort of doing like the things from the past. So maybe that's why now this looks, oh yeah, it's sort of the same. You just have to keep more tracking more variables. But good. Let's do an example. Actually, yeah, sequences and series fortunately don't appear at all in this class. So that's
That would be, oh, no, thanks. I'm glad that it's not in the class.
yeah, that topic is kind of, I mean, it's an interesting topic, but it's sort of it's very weird the way in which it's used in Calc. Calc 2 is kind of a weird class, actually.
Sammy, they come back to haunt us in computer science.
Oh, good. Yeah, they're cute, like sequences, especially, I suppose.
Wait, do sequences come back in differential equations in that class?
Series do come back more. Sequences not that much, but series actually do come back. Yeah. Okay, let's like we have this function. Let's try to find the critical points and classify them. So again, first we find the critical points. In order to find the critical points, you need to find the first partial derivatives, always. So let's try to find the partial derivatives. What's the partial derivative with respect to x? It gives you x squared, and then 2y, and then -6, right? And what's the partial derivative with respect to y? It gives you 2y plus 2x, and then -3, right? Is this okay? And here, like, it's very important to stop just to make sure that like the partial derivatives went well, because otherwise, I mean, it does affect the rest, of the problem. So I think they are fine, right? And you have to set each of them equal to 0. So you have a system of equations.
One second, could you please do the critical points again?
Go up, you mean?
Could you please explain where you got the critical points again? Sorry,
Oh, we still haven't found them. I'm just saying that in order to find the critical points, you need to find the partial derivatives, right? With respect to x and y, and you have to set them equal to 0. So that's what I'm about to do. But the critical points are always found by setting the partial derivatives equal to 0. So that's what we're trying to find. So finding them. Is that making sense? So I'm just saying how to find them. We still don't know which they are, which points they are. So you have a system of 2 equations with 2 unknowns, and now you have to solve it. So how would you solve this system? What's the thing you could do here? You could multiply the second one by -1. You could eliminate the 2y. That's also a nice one. So you see, like, there are like different options. One thing you can do is just like, I mean, say you could try to think of it as a substitution, right? So you can use the second equation. For example, like, again, there are different ways to do this, but you could take the second equation to solve for y. So if you start with the second equation, you can say that 2y equals 3 minus 2x, and then you can say that y equals 3/2 minus x. Is that making sense so far? So good. And again, like, there are many options. This is not the only one option to do this. You could have started also with the first equation and say solve for y from the first equation. So there are other, like, there are alternatives, right? Well, you have to be careful because this is quadratic. So it's not like a, you cannot, this is not like a linear algebra problem, because in linear algebra, you need all the exponents to be one of the variables. Yeah. It's a little bit, yeah, no. That's a temptation, but the system, I mean, right. So I'm making the substitution in the first equation, and that's what I find. So far, so good. Are there any questions about this? And this simplifies to what? X squared minus 2x minus 3 equals 0. And then how do you solve this system? I think they're very close. It's almost that, I think, but let's just start with the, yeah, you factorize. Good. So you factorize here. And now this gives you two possibilities, right? So one option is that x equals 3, right? But if x equals 3, what's the corresponding value for y? Y would be 3/2 minus 3, right? And that gives you minus 1/2, correct? Or what? Minus 3/2. Is that making sense? Because you have to go back to the equation for y that we had in terms of x. So that way you pin down both the value of x and y. And if x equals -1, then you go back to the equation for y, and then this becomes 3/2 minus becomes plus, so 3/2 plus 1, which is 5/2. Is that okay with everyone? So here you got the point 3, -3/2, and here you have the point -1, 5/2. So let me stop here to see, are there any questions up to this point? So far, so good. So how many critical points did we find? 2 critical points, right? So we found 2 critical points. Now we classify them, right? And for classifying them, we need the second partial derivatives. So you need to go back. As you can tell, these problems are long. So you need to go back to the first derivatives. Because, like, I mean, to find the second partial derivatives, you need to know which were the first derivatives, right? So the second partial derivative with respect to x would be just 2x. The mixed one would be 2. And the second partial derivative with respect to y, it would be 2 as well, right? And so you arrange this into, the middle one, remember that meant after you did the partial with respect to x, now do it with respect to y, for example. So I took the partial with respect to x and did it with, and then took the derivative with respect to y. And so if you take the derivative with respect to y of this, you just get 2. Okay, good. And you arrange this into a matrix. So the matrix in this case is what? It is 2x, 2, 2, 2. Is that making sense? Great. So the determinant, right. So you have your 2 by 2 matrix. The determinant of this, right, is 4x minus 4, which is the same as 4 times x minus 1. And now we just have to look at each specific critical point. So let's, what happens at the critical point?
Professor, just one question.
Yes.
Where did the third 2 come from? In
This
h
one,
equals?
this one.
No, in h equals. Yeah. So.
Right. So here you put the second with respect to x, right? Here you put the second with respect to y, and then here you put the mixed ones. But remember that the mixed ones are always the same, so you can just copy. These two are always supposed to be the same, right? It's just that the mixed ones agree. Yeah, the hybrid ones, like.
Thank you.
Yeah, sure. So we had this critical point. This was one of the first, there were only 2, right? Like this is the one, like we have to start somewhere. So for this critical point, what's the value of the determinant evaluated at this critical point? It is what, 4 times 3 minus 1, which is 8, right? Which is positive. This is the only thing you care about, the value of this determinant. Oh, I just mean that this this thing means find the partial derivative with respect to x, you get this function, and now take the derivative of this function with respect to y, and that's how you get the 2. So instead of doing x or y, you do first x and you get here, and then you do the derivative with respect to y.
Professor?
Yeah.
If there was a third variable in this problem, or other variables, then do we just basically grow the matrix by 1 row and column each?
That's what you would do, but not what we're going to do. But yeah, because we are stopping at 2 by 2 matrices. I mean, we're just doing this for the 2 by 2, like the case of 2 variables. But yeah, sure. if you wanted to do this like for more advanced problems, you get like a 3 by 3 matrix, and yeah, kind of it's similar, but it's a little bit tricky. That one does take more time.
Right, then you just need to do cofactor expansions and
yeah.
Okay.
So you find the derivative with respect to x, and then you think of this as a new function, and then you just find the derivative of this new function with respect to y. Yeah. So is that okay? Now, what did I say in the case that the determinant was positive? You go back to our crucial table, and the determinant being positive is a long case. So now we have to look at the sign of the second derivative. Okay. So what's the sign of the second derivative? And the nice thing is that at least we can read the second derivative from the first entry of the matrix. So what's the sign of the second derivative? at this critical point, it would be 2 times x. So it becomes 2 times 3, which is 6. And this is still positive, right? So positive means happy emoji. And that means like it's a relative mean, right? Is that making sense? And then the other one is the critical point, the second critical point that we found. Let's call it Q. And this was -1,5, right? And again, now you look at the determinant, the same determinant, but now at this point Q. So it was 4 times x minus 1, but in this case, it becomes 4 times -1 minus 1. So this becomes -8, right? So what? Good, right? It is negative, right? So this is a negative number. And again, if you go back, sorry, just to go back for a second. If you go back for a second to the case that I told you that the determinant is negative, that means that you get a saddle point. So this one is a saddle point. Is that making sense?
So sorry, can you go over the first one again, the second part where you did the second derivative? Yeah.
Yeah. So the second derivative in general was 2x, right? That was the expression we found for the second derivative. But x in this case is 3, right?
Yes.
So it becomes 6, which is a positive number. And so you do the positive emoji.
And the line above that on the determinant? Wait, yeah, what is the difference between that determinant line and that?
These two?
Yeah.
Well, I mean, the thing is like the determinant, you have to check first. Like having a positive determinant could still mean that you have a max.
Right.
So
right.
The determinant on its own, like the determinant is good enough to say, okay, you're either a saddle or you're max and min, but I'm not good enough to tell you whether if you're max or min, which of the two you are. So that's where you look at the second derivative.
Great, thank you. Okay, yeah, that's just that info from above is still new, I guess.
Right, exactly. You can also do it with respect to the second derivative with respect to y, but you don't like it is equivalent. Like you would get the same information, but it's just easier to do it with respect to x because in Calc 1, like x was usually the name for the variable, right? Oh, yeah. If the determinant is 0, you're done. You just say, I cannot keep doing this. You give up. Yeah. Oh, right. Like these problems, they well, so plugging into the determinant for x. No, there. I mean, the determinant involves a combination. Like in general, the determinant will involve x and y. It's just that in this case, it happens to be simple enough, and so it only involves the variable x. Let's see. Okay, I think a second example would actually. Right, relative mean and local mean. You can take a synonym. Sorry. Let's do a super fast one, but I think this clarifies a little bit more. Let's this one is way too easy, but it's useful still. What are the critical points? Well, you need to find the partial derivative with respect to x, which is just 2x, and set it equal to 0, right? And you also find the partial derivative with respect to y, which is 2y. Right, so the only critical point will be, right, so you need to solve 2x equals 0 and 2y equals 0. And the only thing that this can happen is if x equals 0 and y equals 0, right? So you get 0, 0. Is that okay? So this is the only critical point that appears here, right? Now, say now you want to classify it, right? Now we have to classify it. And for that, remember, you need the second partial derivatives. So what's the second partial? Okay. Let me do it. Let's see. I want the second partial derivatives to involve x. So let's see. Okay, let me make it like this. Okay, I'll do it this way. X cubed plus 3, x cubed plus y cubed is still very easy, but just to make a point about the determinants stuff. It's still only 0, right? So that didn't change too much. So it's still 0, 0 is the only critical point, right? But now what's the second derivative with respect to x? That's 6x, right? What's the second derivative with respect to y? That's 6y, right? And what's the mixed partial derivative? Again, that just means this just means differentiate this function with respect to x and then with respect to y. You can also do it in the reverse order. That doesn't matter, right? But you get 0. Is that okay with everyone? So the matrix, the H matrix is in this case 6x 0, 0, 6y. Is that making sense? And then the determinant, right, of this matrix is 36xy. So I'm just making this example so that you see that this determinant in general can depend on x and y. It's just that it was an accident that last time it only depended on x. In general, it will depend on everything, okay? And what's the value at the origin of this thing? 0. And since so here we landed in the unfortunate case where it's inconclusive, right? So we stop, we cannot classify it. Is that okay?
Can you graph it?
Oh yeah, we can graph it. I can show it to you. Yes. Yeah, we could. Let me open GeoGebra again. I think this one actually is like a saddle point. Like in reality, it would be like a saddle point because it's like a cubic thing. So it's similar to the one variable case because one variable case, it was like a, yeah, I think, let me, oh, yeah, this one is cute. Let's see. Can everyone see it? So the origin is like does everyone see, like, there are like places where you go down and you get to this point, and there are places where you come up and you get to this point, right? So in this case, it would have been like a saddle point. It's just that we don't have the tools to say that, okay? And yeah, let's do another example, but we're now going to spice things up a little bit. I mean, this is definitely the longest topic on the exam, like in terms of if you were actually, like if the problem were solved from beginning to end, this is like the most tedious one. And it's like the one that involves more algebra. So yeah, so if you were doing all these steps, like this is the one that does take the most time. So yeah, let me do another example, but the new added twist now with the twist is like the absolute, finding the absolute max and mean problem. Well, I don't know if the next one will count as obliterating, but it will. Like if you look at the problems on the PDF that I recommended for the quiz, which is not really a quiz because there's no quiz next week, but I sent an announcement recommending some problems. If you look at some of those are long, and so you should work them out. I did write the solutions so you can compare it, but let's do it with an absolute max and mean. So I don't know if you remember from your, again, nice Calc 1 class, that if you had like a closed interval, A and B, that you could like find the absolute max and mean of the function on this closed interval. You basically would evaluate, like to find the max and the absolute max and mean here. You would what you would do is you do like a table or a list that includes the critical points inside the interval AB and the values of the function. Is that okay? Everyone remembers this type of problems? I'm about to do an example like this, but for our version. So in our version, like not to make things too complicated, the only things that you have to worry about is like if the region is like say a triangle or a rectangle. So now you have like, instead of like an interval, right? You have like some region R. So this would be, we are going to do the case where this region is like, you're going to try to find the max and mean of the function over this region. So now the region R is okay, and you do something similar. What you do is you make a list. So here you just make a list which includes oh, it can be another shape, but it would just be too complicated for this class. It can be other shapes. Yeah. The method that, in fact, for that, like the easiest thing would be Lagrange multipliers, but that's not on this exam. It would be on the next one. So fear not. It's just, it would, otherwise it would take forever. So okay, so let me do an example to explain what I mean by that. Okay.
Because the shape is not going to be just a flat plane, it could be like curved. That's why, like, if we took a cross section of that plane, there would be like a curve, and we need to find critical points on it.
You mean like the graph is like this floating blanket, right? Like,
Yeah.
and so if you look at the stuff of the graph above a rectangle, right, you'll see some max and mean, but also it's similar to this picture where like the max and mean can occur at the edges, at the boundaries.
Yep. Okay.
Right. Yeah. Now they're called absolute max and mean. Before they were just called relative. Correct. So let's look at, but I'm just saying it is the same that we did before. It's just now we have to do a little bit more. So let's say that the function is let's try to find the absolute max and mean of for this function. And now the region is this triangle.
What view is this? Is this the XY or the Y?
This is from the XY plane.
Okay.
Yeah, the domain. This is always like the region is always some region on the XY plane. Yeah, because that's where the domain of the function lives. Correct. So let's find first the ordinary critical points of this function. So what are, and this is exactly the same that we were doing last before. So here are the critical points of f. For that, remember, you need the partial derivatives. In fact, like usually I recommend just compute everything from the beginning. Just compute all the, you need 5 partial derivatives, right? Like x, y, x, 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 y, and the hybrid, which are really 2, but they're always the same. So let's compute all the junk from the beginning. So it's 4 minus 8y, right? What's the partial derivative with respect to y? It is minus 8x plus 2, right? And then let's do the other 3 so that we don't have to go back to them. What's the second one with respect to x? That one is 0. Yeah. And then what's the second one with respect to y? That one is 0. This one is an interesting one. And what's the mixed one? That one is -8. Is that making sense? Good, good, good. And then let's solve the system, right? Like the system of equations that we need to solve is these two equations. So we have to set them equal to 0. It's 4 minus 8y equals 0. And then minus 8x plus 2 equals 0, right? And so this one gives you that y equals 1/2, right? And x equals what? 1/4, correct? Is that making sense so far, so good?
Would have been negatives.
So you're moving like you can think that you're adding 8x to both sides, right?
That's right.
Is that okay?
Yeah.
So the only critical point is 1/4, 1/2. Is that making sense? And what is our matrix H in this case? This is why it's good that you computed already all the partial derivatives, the second ones. So it's 0, -8, -8, 0. And look at this, like in this case, it's all constant numbers. So that can also happen. Is that okay? I mean, there are no rules on what you should expect of what the matrix, like coefficients of this matrix should be. Sometimes they don't just depend on X. Sometimes they depend on X and Y. Sometimes they're just numbers, like all those things can happen. And so the determinant of this matrix, well, at the point, at the critical point, 1/4, 1/2. I mean, it's just like, what do you get here? Well, no, remember it's actually -64 because you have to multiply the diagonals and subtract them. Is that making sense? So what should we get? Like, because the determinant was negative, what is this critical point then? It's a saddle point. Good. So if this had been like the previous problems, you would have finished here. This would have been everything, okay? But now comes a new part. So again, just to remind you of what we were working with, we have this triangle, which was 1, 0, 0, 1, right? Somewhere in this inside this triangle is the point 1/4, 1/2. So you see it somewhere in there, right? And then now here's the new part that we didn't do in the previous problems. Now you have to make a list, right? And so your list includes, it includes a couple of things. It includes first the critical point that you found. Then you include the vertices, okay, of the triangle. What are the vertices in this case? The vertices are 0, 0, 1, 0, and 0, 1, okay? And then you include, the last step is that you have to include critical points that you get by looking at the function along each edge. So critical points coming from each edge of the function. And this is like what requires a little bit more explanation. So again, let me remind you what the function was. So this was a function, right? Yeah, the problems only limit the domain. The range is never, the range is just whatever it is, depending on the domain that you were given. Oh no, it was a saddle point because the determinant was negative. So when the determinant is negative, it's a saddle point immediately. So far, is that okay? So again, this was the function, and this was the domain. Let me draw again the triangle. And so the thing is that you have to realize that there are 3 sides to a triangle, right? Yeah, the triangle would be given. Yeah, the triangle or rectangle would always be given. So let's start with the green one. Let's start with the green side. What's the equation of this vertical side? What's the equation of this one? X equals 0, right? So what happens with the function? The function becomes a function, since X is 0 on this side, the function just becomes a function of one variable. Okay, so you can just write 2y plus 1. Is that making sense? Because along this side, X is 0, so you can substitute X with 0 here, and the first 2 terms go away, and then you just get 2y plus 1. But this function as a function of y has no critical points, right? Because the derivative is always non-zero. So here there are no critical points. Is that making sense? Yeah, limiting the range would be a lot more complicated. It's not right. Limiting the range is it is something you would never be asked, but yeah, you have to you will start playing with inequalities involving the function, like the formula for the function. What's the equation of the blue side? The equation of the blue side is y equals 0. So if you plug y equals 0 into the formula for f, right? Only one variable survives. So now this is a function of x, and it's 4x plus 1, right? And finally, here comes the
That's for one question.
yeah.
What
So-
happens to the -8 in the
Oh, this one?
F? Yeah.
Oh, the thing is that you're setting x equal to 0, so this one also goes away.
Oh, okay. You're plugging it in. Okay, never mind.
Right. And but now finally comes the interesting one. What's the equation of the hypotenuse? Yeah, let me write it as 1 minus x, which is the same that you wrote. So this is hypotenuse. Y equals 1 minus x, right? And now the function again becomes a function of one variable. Let me write it. Let me copy again the function so that you can see it more clearly. But if you plug y equals 1 minus x, you get 4x minus 8x 1 minus x plus 2 1 minus x plus 1.
Wait, how did you get 1 minus x?
Well, you have 2 points.
Okay.
Right.
Just do that one.
The point intercept equation, or however that's called. Yeah. Is that okay? So this is the function that you get, which again, if you simplify it a little bit, it gives you 4x minus 8x plus 8x squared plus 2 minus 2x plus 1. And so this simplifies to 8x squared minus 6x plus 3. And finally, if you take the derivative of this function with respect to x, that gives you 16x minus 6. And this one does become 0. This one becomes 0 when 16x equals 6 or x equals 3/8. Okay, and so and if x equals 3/8, then y, which was 1 minus x, becomes 1 minus 3/8, which is 5/8. So at the end of the day, oh, we're close to finishing. I promise, we're almost there. So at the end of the day, if you go back to the triangle, if you return to our original triangle, we had found at the very beginning of the problem this point 1/4, 1/2. Then we just found this point on the hypotenuse, which is 3/8, 5/8. And then I'm saying that we are going to make a table that includes these two together with the vertices. So 1, 0, 0, 1, and 0, 0. And so we make a table that has the point x, y, and then that has the value of the function. And then you just include everything. So you copy everything. So you put 1/4, 1/2. If you evaluate the value of the function at that, yes, gives you 2. If you plug in those values for x and y, you get 2. If you plug in 0, 0, I mean, let me put the one that if you plug 0, 0, which are let me put different colors for what we're doing. So this was the original critical point. If you plug in 0, 0, you get 1. If you plug in 1, 0, you get 5. If you plug in 0, 1, you get 3. And then there was this last one, which we've just found recently, which is 3/8, 5/8. And if you plug this one up, you get, I mean, it's a little bit, I mean, it requires some simplification, but you get 15/8. So which of all of these numbers do you see? No, I did this a long time ago. So which is of all these numbers do you think is the largest one? Which is the largest value here? 5. So good. So that means that this is a point that yields the max, the absolute max. Good. And what's the smallest value of all of them? Yes, 0, 0 is the mean. Woo. Just in time. Yeah, although in practice, like, I mean, like this is a long problem. So usually probably like it gets simplified in the way it would be asked. Like you could be given like some critical points. Like you may not be asked to find all of these from beginning to end, right? You could be asked to, you could be told, oh, by the way,
Yeah,
critical point, like
I understand.
yeah.
I
And
was gonna
probably
say,
the
I
questions would
understand
be,
that, like,
yeah.
on tests and stuff, I understand you give us like sections of the problem and you give us some starting information.
Exactly. Yeah. I mean, because this on its own is almost like 30 minutes, it would be like half the exam. But the graph, the triangle would be part of the information that's given. The graph is not necessary. You don't need to know the graph. So that would not be given because like the point is that like this computations tell you what would be the max and the mean and etc. But I mean, so there are more examples that I do in detail on the PDF that I mentioned on the announcement. And then I'll send you the link to the YouTube videos. I also did some other examples there. But yeah, you should, you have, I think the exam, okay. So I would hope, actually, I do think that this exam, I would be surprised if the grades are not better. Like that's how I would put it, because I think it will seem more familiar. So if not, you can come for it. Since it's Halloween, you can come trying to burn me like in the Salem witch trials. Although I'm not, we're not physically close, so I'm like, I don't know how much of a promise that is. Yes, yes, so I was surprised by that, but I mean, precautionary, more measures have been taken. I thought that, yeah, I mean, in our class, it went better than in other classes, but still, I mean, I think this time, yes, I can. It should be more, yeah, I think the writing is more like, yeah, I think that's true. It does, I think it would look more familiar, yeah. No, because we don't, I mean, like, again, it like motivate, like, people should like feel motivated to continue on the course. So hopefully, I think this should go better. Yeah. But it's like free will. There's still some sort of free will at this moment, so you should still prepare as much as you can, whatever, like for the exam on Monday. So I'll see you on Monday, but I'll send you the link with the extra office hours. Bye. No, I didn't have plans for that. I didn't even know about it. Yeah. Oh. I live in New York, actually. So I wouldn't have been able to see it anyway. So you too. Good.